Hi, today we're going to talk about the Arrhenius equation. In order to understand what the Arrhenius equation is, I want you to think back to what you learned about collision theory and the factors that affect a chemical reaction. Now, if you'll remember, one of those was temperature. So the question we want to address today is there a way we can quantify how temperature affects the rate of reaction? Now, of course, since I'm asking that question, the answer is yes. And the equation we use to do that is the Arrhenius equation. Now, this is one form of the Arrhenius equation, what we call the exponential form. Let's look at what each of these variables represents. And let's start off with the thing that's probably most familiar, which is the temperature in Kelvin. We also have the gas constant, and since we're talking about energies here, we'll use the value of 8.314 joules per mole Kelvin. So RT, you'll see those two factors together a lot in the next few weeks. Then what we have is the activation energy. We know that molecules need to collide with enough energy to overcome the activation energy, and the higher the temperature, the more likely that is to happen. So that's why the activation energy and the temperature are in the same term. The last thing on the right side is this factor that we call the frequency factor or the exponential factor. It does have a physical meaning, but it's not something that we care too much about at this stage of kinetics, so let's just ignore that for now. So all of these combine to give us the rate constant. Now, the exponential form of the Arrhenius equation is super useful in lab. In fact, you're going to use it during one of your labs later on. And I'll talk about that more in the lab video. But what we're doing now is not experimental kinetics, we're just doing calculations. And so we're going to transform this into the 2-point form of the Arrhenius equation. I did tell you that we're going to see more things like this, right? Anyway, as you can see, this is pretty similar to the 2-point form of the Clausius-Clapeyron equation, with a couple of important differences. On the left side, we have the natural log of a ratio, only this time it's the ratio of two rate constants rather than the ratio of two pressures. On the right side, instead of the heat of vaporization divided by R, we now have the activation energy divided by R. And then we have the difference between the inverses of our temperatures. So again, slightly different, but basically the same format. So, a few tips for using the Arrhenius equation. These are going to look very familiar because they're quite similar to what we used when we did Clausius-Clapeyron. First, remember to figure out which is your condition 1 and which is your condition 2. In this case, you're going to try to identify pairs of rate constants and temperatures that belong together. Second, make sure you use the correct value of R. Again, we're dealing with energies, so that's going to be 8.314 joules per mole Kelvin. Third, check to see if your units match. In this particular equation, the only real mismatch you're likely to have is between kilojoules in the activation energy and joules in the gas constant. And then we have our usual disclaimers. Write down your calculations as you go and don't round until the very end. So let's look at a couple examples of how to use the Arrhenius equation. In this problem, let's first read and see if we can identify the rate constant and temperature pairs that we need to find an answer. So here's one pair, a rate constant that's 0.0031 per second at 10.5 degrees Celsius. And then here's something that's associated with a temperature, but it's asking what that rate constant will be at 35 Celsius. So what this means is the rate constant is our unknown in this problem. So I'm setting the stuff outlined in blue to be K1 and T1. Again, calculating the temperature in Kelvin, even though it's given to me in Celsius. So we know both K1 and T1. We know T2, but we don't know K2. And once again, the disclaimer that it doesn't matter which one is K1, T1, which one's K2, T2. You could swap these and still get the same answer. The second thing we need to do is make sure we plug in the correct value of R for the gas constant in our equation. So we'll plug that into our equation right now, as well as all the other stuff we know, K1, T1, T2, and the activation energy given in the problem. And then the third thing is to check to see if your units match, which they don't. We have kilojoules for the activation energy and joules for R. So I'm going to convert kilojoules into joules. And now, because we're running out of room, I'm going to go on to a new slide where I will do some simplification. Let's start with everything on the right side. That equals negative 3.07644. And that's equal to the natural log of our K1 value, 0.0031 per second, divided by K2. To get rid of that natural log, you need to use the exponential function and do e to both sides. So what we get is our ratio of rate constants being equal to e to the minus 3.07644. And solving for K2, we get this expression. Run it through the calculator, and we get that K2 equals 0.067 per second. Now, you always want to ask yourself if your answer makes sense. Remember, T2, 35 Celsius, is higher than T1, 10.5 Celsius. And we know that the rate of a reaction will increase as the temperature increases. So our answer for K2 should be larger than our K1 value, and it is, by a factor of about 20. So let's do one more problem. In this problem, we're going to find the activation energy. And again, we're going to start by looking for our KT pairs. Here's one pair that's associated with 25 Celsius, and here's a pair that's associated with 55 Celsius. Let's plug all of that information into our equation and see what we can simplify. So what I've done here is I've simplified everything on the left side. That would give us negative 3.8275. And then on the right side, I've simplified this section in parentheses to be this tiny negative number. And so now that we've just got a bunch of numbers and the activation energy, we can rearrange so the activation energy is on one side and everything else is on the other. Plug it into your calculator and you get an activation energy of 103,779 joules. I'm going to convert that into kilojoules, not because I need to, but because it's a convenient way to get the right number of sig figs, so we end up with 104 kilojoules. So the Arrhenius equation is really useful if you know the rate constant at one temperature and want to figure out what it is at another temperature. And it's always really useful for calculating activation energies because there's no way to actually determine those directly. I hope this was useful, and I'll see you again soon.